Welcome to Blueprint to Reality, your go-to channel for unraveling complex engineering concepts and making them easy to understand. Today, we're exploring an essential topic in engineering, structural dynamics. This field is all about how structures respond to forces that change over time, like wind, earthquakes, or even nearby traffic. Let's dive in and see why understanding structural dynamics is crucial for designing safe, resilient structures. What is structural dynamics? So, what exactly is structural dynamics? Structural dynamics is the study of how structures behave when faced with forces that vary over time. Unlike static forces, which are constant, dynamic forces fluctuate and can cause structures to vibrate, sway, or oscillate. Think of a bridge moving with passing cars or a skyscraper swaying slightly in the wind. Structural dynamics helps engineers predict and control these movements, keeping structures stable and secure. Key concepts in structural dynamics. Let's break down some key concepts in structural dynamics, starting with natural frequency. Every structure has a natural frequency, an inherent rhythm at which it vibrates. If an external force, like wind or seismic activity, matches this natural frequency, it can cause the structure to resonate. Resonance amplifies vibrations and, if unchecked, can lead to structural damage or failure. Then there's damping, which acts like a brake system for vibrations. Damping is a structure's ability to absorb and dissipate energy, preventing vibrations from escalating. This concept is vital for controlling movement in tall buildings, bridges, and other structures that are constantly subjected to dynamic forces. Applications in real-world scenarios. Why does this all matter? Structural dynamics is critical for designing buildings that can handle real-world challenges. For example, in earthquake-prone regions, engineers use dynamic analysis to ensure structures can absorb and withstand seismic energy without collapsing. In skyscrapers, they use tuned mass dampers, large counterweights that reduce swaying caused by high winds. These damping systems make tall buildings safer and more comfortable for occupants. How engineers analyze structural dynamics. How do engineers actually predict a structure's dynamic response? They rely on mathematical models and simulations to calculate how different forces will impact a structure over time. Techniques like modal analysis help identify which parts of a structure might vibrate most and at what frequencies. This analysis is crucial for spotting potential weaknesses and optimizing designs to prevent failure. Conclusion. In summary, structural dynamics is all about ensuring our buildings, bridges, and towers can withstand the unpredictable forces they encounter. By understanding and controlling these dynamic responses, engineers create structures that are not only resilient but also safe and comfortable. Thank you for watching Blueprint to Reality. If you enjoyed this look into the world of structural dynamics, please like, subscribe, and hit the notification bell for more engineering insights. And let us know in the comments, what engineering topic would you like us to cover next? See you in the next video. Welcome to Blueprint to Reality. This is your go-to channel for unraveling complex engineering concepts and making them easy to understand. Today, we're diving into a timely and critical topic, the impact of climate change on structural engineering. As extreme weather events increase and environmental patterns shift, engineers are faced with the challenge of creating resilient structures. So, how is climate change influencing structural design? Let's break it down. Understanding climate change in structural engineering. First, let's define what climate change means in the context of engineering. Climate change brings a rise in sea levels, higher temperatures, increased storm frequency, and other severe weather events that can impact the longevity and safety of structures. These changing conditions mean engineers must anticipate new risks and incorporate innovative solutions to ensure that buildings and infrastructure can withstand more extreme and unpredictable climates. Rising sea levels and coastal engineering. One significant effect of climate change is rising sea levels. For structures near coastlines, this means an increased risk of flooding and erosion. Engineers are adapting by designing buildings with elevated foundations, using materials that resist water damage, and constructing barriers like seawalls to protect against encroaching tides. These measures are critical to keeping coastal cities and communities safe as water levels continue to rise. extreme weather events, and building resilience. Climate change is also bringing more frequent and intense storms, hurricanes, and heat waves. These events put enormous stress on buildings, particularly high-rise structures and bridges. Engineers now need to account for stronger winds, heavier rain, and higher temperatures. For example, buildings in hurricane-prone areas might require reinforced frames or advanced anchoring systems to prevent collapse in high winds. And in areas with extreme heat, materials must be chosen to withstand thermal expansion without cracking or degrading. Material innovations for climate resilience. The need for climate-resilient structures has driven innovations in materials. Engineers are turning to materials that can handle these new environmental stresses. For example, high-performance concrete and steel alloys are increasingly used for their ability to withstand harsh conditions over time. Additionally, more sustainable materials like bamboo and recycled composites are gaining popularity as engineers seek eco-friendly ways to make buildings stronger against environmental changes. Adapting infrastructure for temperature fluctuations. Climate change is also causing greater temperature fluctuations, which can affect infrastructure like roads and railways. When temperatures swing between extremes, materials expand and contract more frequently, leading to cracks and other structural weaknesses. Engineers now design with these variations in mind, using flexible materials and expansion joints to accommodate temperature changes without compromising stability. This adaptability is crucial for extending the lifespan of infrastructure. Advances in predictive modeling for climate risks. One exciting advancement in engineering is the use of predictive modeling to anticipate climate-related risks. Using data on climate trends, engineers can simulate how a structure might perform over decades, considering factors like storm surges, wind speeds, and rising temperatures. This helps engineers refine their designs to be as resilient as possible, making climate risk-informed decisions even before construction begins. Conclusion. In summary, climate change is reshaping the way engineers design and build structures. By adapting to rising sea levels, preparing for extreme weather, using resilient materials, and implementing predictive modeling, engineers can create buildings and infrastructure that stand strong in a changing world. Thanks for tuning in to Blueprint to Reality. If you found this discussion on the impact of climate change on structural engineering insightful, please like, subscribe, and hit that notification bell for more engineering insights. And let us know in the comments, how do you think climate change will continue to influence engineering? See you in the next video. Welcome to Blueprint to Reality. This is your go-to channel for unraveling complex engineering concepts and making them easy to understand. Today, we're focusing on a critical aspect of structural engineering, wind tunnel testing. As our world becomes more urbanized, understanding how wind affects buildings and structures is more important than ever. So, why is wind tunnel testing essential for engineers? Let's find out. Understanding wind tunnel testing. First, let's define what wind tunnel testing is. A wind tunnel is a controlled environment where engineers can simulate and study the effects of wind on various structures. By creating airflow around models, often scaled-down versions of buildings or bridges, engineers can observe how wind interacts with these designs under different conditions. This testing provides valuable data on factors such as wind pressure, turbulence, and potential vortex shedding. Wind tunnel testing is particularly important for high-rise buildings and structures in windy areas, where the forces exerted by wind can significantly impact stability and safety. Through testing, engineers can identify weaknesses in a design and make informed decisions to enhance resilience against wind forces. Applications of wind tunnel testing. Now, let's explore some key applications of wind tunnel testing in engineering. One primary use is in the design of tall buildings. As structures reach greater heights, they become more susceptible to wind forces. Engineers use wind tunnel tests to analyze how wind flows around the building, helping to optimize its shape and structural elements to minimize stress. For instance, iconic skyscrapers like the Burj Khalifa and One World Trade Center underwent extensive wind tunnel testing to ensure they could withstand extreme gusts. This data is crucial for determining the appropriate materials and construction techniques to ensure safety and comfort for occupants. Wind tunnel testing is also essential for bridge design. Engineers evaluate how wind interacts with bridge components, such as cables and decks, to prevent phenomena like flutter or sway, which can lead to catastrophic failures. The Tacoma Narrows Bridge is a famous example of what can happen when wind effects are not adequately considered. Advancements in wind tunnel technology. Looking ahead, advancements in wind tunnel technology are revolutionizing how engineers conduct testing. Traditional wind tunnels are often large and require significant resources, but smaller, more efficient options are now available. Computational fluid dynamics, CFD, simulations can complement physical wind tunnel testing, allowing engineers to analyze airflow with high precision and at a fraction of the cost. These simulations enable engineers to test multiple design variations quickly, making the design process more efficient. By combining CFD with wind tunnel data, engineers can achieve more accurate predictions of wind behavior, leading to safer and more efficient designs. The role of wind tunnel testing in sustainability. As sustainability becomes increasingly important in engineering, wind tunnel testing also plays a role in developing energy-efficient buildings. By understanding wind patterns, engineers can optimize building orientation and natural ventilation, reducing reliance on mechanical heating and cooling systems. This not only lowers energy consumption but also enhances occupant comfort. Additionally, wind tunnel testing is essential for assessing the impacts of new constructions on their surroundings. Engineers can evaluate how a new building will affect wind flow in an area, ensuring that it does not create wind tunnels or uncomfortable conditions for pedestrians and surrounding structures. Conclusion. In summary, wind tunnel testing is a vital tool in engineering that ensures the safety, stability, and efficiency of structures. As our designs become more ambitious, understanding wind behavior will be crucial for creating resilient buildings and infrastructure. Through advancements in technology and testing methods, engineers can continue to innovate while prioritizing safety and sustainability. Thank you for joining us on Blueprint to Reality. If you found this discussion on the importance of wind tunnel testing insightful, don't forget to like, subscribe, and hit that notification bell for more engineering knowledge. We'd love to hear your thoughts in the comments. How do you see wind tunnel testing shaping the future of engineering? See you in the next video.